Okay, so this is where we're going to look at some more advanced gases type of problems. And so the one that we're going to try to focus on is we're going to look at some of this with our partial pressures. So let's look at these 5 balloons. So for these 5 balloons, each one is filled to the same volume at 25 degrees Celsius and 1 atmosphere. And so we want to know which one contains the greatest mass of gas. Now, if we assume that they all behave ideally, there's a couple things that we want to think about. If we have PV equals nRT, and for each of them, if the pressure is the same, the volume is the same, and their temperature is the same, well, if we set that up as P1 V1 equals N1 T1, we could get P2 V2 equals N1 T2, or sorry, N2 T2. And we could do this for all 5 of them if we wanted to. But when we start to look at that, if the pressures are the same, then we can remove the pressure from all of them. If their volumes are the same, we can remove the volumes from all of them. And if their temperatures are the same, we can remove their temperatures from all of them. And what this is going to tell us is that their moles are all the same. If the gases behave ideally, then if all 3 of the other conditions are the same, then the 4th condition also must be equal to itself. So that means that each of these balloons has the same amount of gas in terms of moles. Now, that doesn't mean that all of their masses are going to be equal, because each gas has a different conversion from its moles to its grams. And remember, that's called our molar mass. So if they all have the same number of moles, then the one that's going to have our greatest mass is going to be the one that has the largest molar mass. And so let's look at their molar masses. Now, since we don't have to do since we don't have to do a lot of quantitative work with this, we can just get some qualitative values. So helium has a molar mass of 4, nitrogen 28, CH4 is 16, O2 is 32, and CO2 is 32 plus 12, so 44. So the balloon that should have our greatest mass is going to be carbon dioxide, has the greatest mass, and then we should explain that. So there should be a because. Each balloon has the same numbers of moles of gas, and CO2 has the largest molar mass, giving it the largest mass. Perfect. And so now we should look at our next one. Well, compare the average kinetic energies of the gas molecules in the balloon and explain. Now, average kinetic energy, whenever we hear that term, it should bring up a translation for us. And that translation is temperature. Now, kinetic energy is those molecules bouncing around. And though that kinetic energy can depend on the mass and the velocity, but how we measure the average kinetic energy is by measuring the temperature of something. So if we look at all of these gases, if they're all at the same temperature, then we need to compare the average kinetic energies. So you might want to say, well, CO2 is largest, and so it's going to move slowest, which is fine, but that's its velocity. And so if we were comparing velocities, then that's what we could be looking at. Instead, though, we're comparing their average kinetic energies. And so in this regard, since they're all at the same temperature, then they all have the same average kinetic energy. Because our temperature is us actually measuring that value. And so them being at the same temperature gives them the same average kinetic energy. Which balloon contains the gas that would be expected to deviate most from behavior of an ideal gas? And so for that, there's two things that we want to be considering. We want to think about molecular size and attractive forces. Now, we don't know enough to talk about attractive forces yet. So the only one that we can really talk about is molecular size. And so the reason why we haven't talked about attractive forces yet is that's still coming up in the later on this semester. And so later on, when you guys see this question, you'll be able to talk about both of them. But if we are only looking at one, then we should talk about the one that we know. And so we could say something like CO2 should deviate from the ideal gas behavior the most because it has the largest molecular size. So the volume of the gas molecules will make the largest impact. Something like helium, which is our smallest one, it's got a molar mass of 4, is going to make our smallest deviation because it's not contributing as much volume to it. Now, looking at our next part, it says 12 hours after being filled, all the balloons have decreased in their size. And so that's definitely something we see. If you've ever had a helium balloon before, then it definitely decreases in its size as time passes. So, predict which balloon will be the smallest. And so we can think about this. Now, our particles are moving around, and so we can kind of think about, well, which one is going to matter the most? Now, there's a law that you kind of be looking at for this, but we can also think about it in terms of their speed that they move around. And so we can think about what we know about the movement of our particles. So we know that the larger their mass is, or their molar mass, then the slower the velocity is going to be at the same kinetic energy. So that means that looking at our 5 gases, the one that has the lowest molar mass, helium, is going to be moving around the fastest. And that means CO2, the one that was the largest, is going to be moving around the slowest. And so if we think about how things diffuse, so that's them moving around and escaping from our balloon, then the one that moves the fastest is going to give it the highest rate. So the balloon that we think that's going to escape the most is going to be our helium, as it has the highest velocity at the same average kinetic energy compared to the other gases. So it will diffuse the fastest. And so that's kind of what we're looking for. things that are moving around the fastest mix the most. And so they're going to be the ones that are easiest or more likely to leave from that container. There is a law that's related to this. It's called the rate of effusion. And so for one gas 1, divided by the rate of the effusion for gas 2, it's equal to the square root of the molar mass of your gas 2 over the molar mass of your gas 1. And so it's the idea that the lower your molar mass, the fastest you move, the faster you move, then the faster you can diffuse. And so that's it for these ones. The next worksheet that you guys are going to be looking at is this super problems one. And so go ahead and fill this one in first. And then if you haven't looked at our gas demo lab, then you want to make sure that you take care of that before you guys get started with your super problems. That's just because on this first one, a lot of what we're doing is very similar to what we did in the gas demo. So you want to be looking at that.